This is the recorded lecture for Chapter 6, Part B slides on bones and skeletal tissues. And we're starting with section 6.5. Let me get the highlighter. Your first term is ossification or osteogenesis. And that is, both of those terms mean bone tissue formation. Bone tissue formation. So ossification and osteogenesis occur when the bones are developing. It begins when the skeleton begins to develop at about 2 months prenatal, and then bone growth continues. The growth of bone continues until early adulthood. And then bone remodeling and repair are lifelong processes. So there are two types of ossification. There's endochondral ossification, which is the process that forms long bones, like the bones of your arms and legs. Then there's intramembranous ossification, which is the process that forms like your skull bones, for example. So in endochondral ossification, bones start out as a cartilage model. So the entire bone is composed of cartilage, and then that cartilage is replaced with bone tissue. In intramembranous ossification, the bone tissue begins developing within a fibrous membrane. They're called membrane bones. So endochondral ossification starts out with a hyaline cartilage model. And here's the process. In step 1 of endochondral ossification, you have the entire bone is hyaline cartilage, and you have a primary ossification center, which begins developing in the center of the where the diaphysis would be. In step 2, you have calcification occurring at that primary ossification center, and then the cavity starts to develop. And you also see the development of bone in the diaphysis. So the center and the outsides of the diaphysis are, the cartilage is being replaced with bone tissue. So you've got bone tissue forming here, cavity forming here. But the first thing that has to happen is the cartilage cells have to get larger, and then they die, and then bone cells replace them. So in step 3, you see the spongy bone begin to form, and blood vessels begin to invade the spongy bone tissue. In step 4, you see the formation, the beginning of a medullary cavity. So what's going to happen is, as this bone grows longer, the cavity will have to get longer and wider too. So you'll have to have osteoclast breaking down bone tissue along the sides and the top and bottom of the cavity. And then bone will have to be deposited outside that cavity. So osteoblasts will be depositing bone matrix as osteoclasts are breaking down bone matrix to form that cavity and to help the bone to grow longer. The critical step that happens the critical event that happens at step 4 are the formation of secondary ossification centers, and those form in the epiphyses. And step 5, the epiphyses ossify or fill in with bone tissue, and the only cartilage that remains is the articular cartilage that lines the ends of the bones, and the hyaline cartilage that forms the epiphyseal plate, and that will stay there until the bone has reached its full growth. Now, intramembranous ossification is going to be how the skull bones form. So it's going to form the frontal bones of the skull, the parietal, occipital, temporal, and then your clavicle bones, which are your collarbones. So intramembranous ossification will begin with mesenchymal cells, and so basically this is what you have: mesenchymal cells cluster and differentiate into osteoblast, and those osteoblasts form an ossification center, and the bone just starts at that center and grows outward. And as osteoblasts secrete bone matrix around them, now that they're trapped inside their cavity or lacuna, they're now an osteocyte, and that process just keeps on. And you end up with the rods or plates called trabeculae forming, and you have the formation of spongy bone, and then compact bone will replace spongy bone on the outer edges of the bone tissue. Okay, there's a section here on the growth and length of long bones and kind of what happens with the epiphyseal plate. The epiphyseal plate, or the epiphyseal cartilage, consists of 5 zones: the resting zone, the proliferation zone, the hypertrophic zone, calcification zone, and then the ossification zone. The resting zone is the area of cartilage on the epiphyseal side that's pretty inactive. So that means it's closer to the epiphysis, not closer to the diaphysis. So that's the cartilage on the epiphyseal side, and it's pretty inactive. Okay. Then there's the growth or proliferation zone, and that is on the diaphysis side. And then you have the hypertrophic zone, which is the area with older chondrocytes closer to the diaphysis. So the hypertrophic zone is the area with older chondrocytes that is closer to the diaphysis. And then the calcification zone is the area where the cartilage matrix is calcifying. It's the chondrocytes are dying, which is the cartilage cells. They're dying and filling with the calcium phosphate matrix. And then the ossification zone is the area where ossification is occurring, and that zone is replaced with spongy bone. And it's the area where the medullary cavity is forming. So you can see in this picture, the resting zone would be closer to the epiphysis, be closer to here. And then the proliferation zone would be under that, the hypertrophic zone. And the reason it's called hypertrophic is the cartilage cells are getting larger. They're hypertrophying. They're getting larger. And then the calcification zone. And then the ossification zone is the closest to the actual diaphysis. So ossification is the closest to the diaphysis, and the resting zone is closest to the epiphysis. And when the individual has reached their full adult height, when they're fully grown, the epiphyseal plate will close, and what's left is called an epiphyseal line. This happens in males around 21 years old, and it happens in females around 18 years old. The growth and thickness of bones happens throughout life. Bones can thicken in response to muscle activity or added weight. And that's growth and thickness is appositional growth. Growth and thickness of bone is appositional growth. So that can occur throughout a person's life to some extent. hormonal regulation of bone growth. So the most important hormone that regulates bone growth is called growth hormone. And growth hormone stimulates epiphyseal plate activity in infancy and childhood. Then thyroid hormone modulates the activity of growth hormone. And testosterone in males and estrogen in females at puberty promotes growth spurts. The end of the growth spurt is the closing of the epiphyseal plate and the forming of the epiphyseal line. All right, section 6.6 is on bone remodeling. About 5 to 7% of bone is recycled each week. So all of our spongy bone tissue is replaced every 3 to 4 years, and our compact bone is replaced every 10 years. So our entire skeleton is replaced around every 10 years. Bone remodeling consists of bone depositing and bone resorption. So breakdown. Remember, bone depositing is putting down more new bone tissue, and bone resorption is breaking down bone tissue. The osteoclasts are the ones that function in bone resorption. And when they do that, when they break down the bone tissue, that releases calcium into our blood. So it raises our blood calcium levels. And osteoclasts are activated by PTH, or parathyroid hormone. Okay. So the hormonal controls of bone remodeling involve parathyroid hormone and calcitonin. It's basically a negative feedback loop that controls blood calcium levels. And it works like if your blood calcium levels are low, then parathyroid hormone is released. So parathyroid, or PTH, is released in response to low blood calcium levels. And what will happen is once you release PTH, your osteoclast will begin to break down bone tissue and release calcium into your blood, and that'll raise your blood calcium levels. And then calcitonin is produced by the thyroid gland. So parathyroid hormone is the parathyroid glands, and then calcitonin is the thyroid gland. So calcitonin is opposite. It is released when your levels of calcium in your blood are high. And basically it would stop the activity of the osteoclast and increase activity of osteoblast. So here's an illustration of how PTH works. In response to the imbalance is that your blood calcium levels are too low. You've got calcium ions in your blood, and the levels of those calcium ions are too low. We need calcium ions for nerve impulses and for muscle contractions. So when we don't have enough, it affects our ability for our muscles to contract and our nerves to conduct. So low calcium levels leads to our parathyroid glands release PTH, or parathyroid hormone, and that stimulates osteoclasts to break down bone tissue, and that raises blood calcium levels. And then I guess they don't have the other. The opposite of that. But anyway, calcitonin would do the opposite of that. Calcitonin would be released when the calcium levels were too high, and it would inhibit the osteoclast, and it would stimulate osteoblasts to build more bone tissue, to remove calcium from the blood and add it, to form bone matrix. All right, so conditions involving blood calcium levels. Hypocalcemia is low blood calcium, and that can cause your muscles to become hyperexcitable. Hypercalcemia is high levels of calcium, and that can cause non-responsiveness. So both low and high calcium levels in the blood are could be deadly. Other hormones that play a role in bone remodeling is leptin. Leptin is released by adipose tissue or fatty tissue and could possibly inhibit osteoblast. So it would inhibit the formation of bone matrix. And then serotonin is a neurotransmitter that regulates mood and sleep, and that can interfere with osteoblast activity also.
Methyl synthesis with serotonin.